Now that we've refined the idea of distance, let's talk about the idea of betweenness. So what does it mean to be between? So I want to talk about a point B that lies between points A and C. And this is how we denote it, this parentheses ABC. And the order is going to be important here, the fact that B lies between A and C and the fact that B is in the middle here. So in order for this to hold, we need two things to be true. We need our 3 points to be distinct collinear points, so they all have to be different points, and collinear, they all have to lie on a single line. And then the other one, the distance from A to B plus the distance from B to C has to be equal to the distance from A to C. And this is how we say something is between. So let's look at this a little more. So if we have ABC, so B is between A and C, then we know the distance from A to B plus the distance from B to C is equal to the distance from A to C. We also know distance is symmetric. So I can rewrite it. Instead of AB, I can write BA. Instead of BC, I can write CB. And instead of AC, I can write CA. We also know the order of addition doesn't matter. So once again, I can rewrite this as CB plus BA equal to CA. So the distance from C to B plus the distance from B to A is equal to the distance between C and A. And this actually shows me that this is the same as saying that B is between C and A. So while the order that we write the between in matters in the sense that B is in the middle, we can read it both right to left or left to right. And both of those will be equivalent. So ABC is equivalent to CBA. Let's start to look at 4 points. Let's suppose we have ABCD, all 4 collinear points. We're going to suppose all 4 of these hold. We have B between A and C, B between A and D, C between A and D, and C between B and D. Then we have ABCD. So A and D are on the outside, B and C are in the middle, and like I said, order matters. We can read this forwards or backwards, but the main thing is if we read them along the line, we have A and then B and then C and then D. So this may seem excessive on why we need this many things to hold in order to do this. So let's dive into that a little more. So if we have the ABC and BCD, why isn't that enough to hold ABCD on a line? When dealing with a sphere, the lines are great circles. So I'm going to consider this circle to just be a line that's on this imaginary sphere. So if we have a point A, a point B, and a point C, so I have the ABC holds, I can put D over here to get that ABCD holds, or that I can get BCD holds. So now I have ABC and I have BCD. However, I don't have ACD. So this actually doesn't work. So even though it really seems like these two should be enough, because of the sphere, these two are not enough, and we actually need to have more betweenness relations than just these two bare minimums. While 2 is not enough, 3 really is. So we have this theorem. If ABC, ACD, and ABD, then BCD and therefore ABCD. So essentially it just says we really just need these first 3. The 4th one will be implied, and then that will give us the entire sequence ABCD. So let's see if we can actually prove this. So the first thing we have is we're going to consider ACD. 0 has to be less than the distance between C and D. So CD has to be greater than 0 since all of these are 4 distinct points. CD is equal to AD minus AC. So this comes from the fact that we actually have AC plus CD is equal to AD. Subtracting AC from both sides gives me my next equality. And this has to be strictly less than the distance between A to D because we have AD minus something, so minus is making it a little bit smaller. And the distance between A to B has to be less than or equal to alpha. And all this was to tell us that the line between C and D is equal to the line between A and B. We needed the distance between C and D to be strictly less than alpha in order for this to work, but now I have a line between A and B that contains C, and then a line between A and B that contains D. Since these 2 points are strictly less than alpha, their distance is strictly less than alpha, we can say that these are the same lines. So that tells us that all 4 of these points are collinear. So that was the first thing that we needed, that they all 4 actually did lie on the same line. The next thing we're going to use, the fact that ABD, that we know that BD is equal to AD minus AB. Once again, writing out my betweenness thing, that AB plus BD is equal to AD, and then subtracting accordingly. We also know that ACD, that tells us that AC plus CD is equal to AD, and so I'm going to substitute this thing into the AD that I have here on the left. So now I substituted in for AD, I did the AC plus CD. I also used my relationship ABC to get the AB is equal to AC minus BC. And now I can see that those ACs are going to cancel. Once I simplify this, I get that BD is equal to BCD. So that tells me that I have BCD, which is what I needed. Now that I have all 4 of my relationships, I'm guaranteed to get ABCD. One more. If the triangle inequality holds, we can actually cut it down further and get that we just need ABC and ACD. So the first thing we need to prove is that these are all collinear. And that's going to follow the exact same as my last proof, so I'm not going to go into it, but it follows exactly the same as we did it in the last proof to prove that these 4 points are collinear. Since we know the triangle inequality holds, we can say that AD is less than or equal to AB plus BD. From the triangle inequality, we also have that BD is less than or equal to BC plus CD. We're going to add AB to both sides of this. That gives us that AB plus BD is less than or equal to AB plus BC plus CD. Well, since ABC, we know that AB plus BC is equal to AC. Since we also have that ACD, we know that AC plus CD is equal to AD. So now I have that AB plus BD is less than or equal to AD. But from my first statement up here, I also know that AD is smaller than this. So if it's less than or equal to and greater than or equal to, it must be equal. So that tells me that AB plus BD is equal to AD, which means that ABD, and using my previous theorem that I just proved, that gives me all 4 of them. So we know that the line is ABCD.